Hello everyone, this is a presentation on structures of LED presented by myself Arpita Bhattacharjee and Misbahur Rahman. This is the contents of our slides. First we have introduction, then types of LED structure, planar LED, dome-shaped LED, surface emitting LED or SLED, edge emitting LED or ELED, superluminescent LED, homostructure LED and heterostructure LED. So this is the introduction. An LED is a PN junction diode which consists of two leads. When a voltage is applied across the leads, electron-hole recombination takes place, which in turn releases energy in the form of photons. This effect is called electroluminescence. So here are some desirable characteristics of an LED. First is it must have an appropriate band gap energy. The material must be suitable for both N-type and P-type semiconductors. And the radiation path of the material must be transparent to the emitted wavelength. So these are there are basically 5 types of LED structures. So we have planar LED, dome-shaped LED, SLED or Birus LED, edge emitting LED and superluminescent LED. So first we have planar LED. The planar LED is the simplest of all the LED structures, which is fabricated by either liquid or vapor phase epitaxial process. Here a p-type diffusion into a n-type substrate to create a PN junction. Only a limited amount of light escapes the structure because of the planar structure of the LED, and therefore the radiance is very low. So here are some disadvantages of planar LED. Due to the planar structure of the LED, only limited amount of light will escape from the LED structure due to total internal reflection, and therefore the radiance is very low. So in order to solve this problem, the shape of the semiconductor is made into a dome shaped or hemisphere, so that the light strikes the surface at an angle less than the critical angle and therefore does not suffer total internal reflection. So we have to overcome the disadvantage of the planar LED, we have dome-shaped LED. In dome-shaped LED, the reflection losses are minimized by changing the structure of the LED into a hemispherical dome. The radius of the dome is chosen so as to maximize the internal radiation reaching the surface of the LED within the critical angle of the LED material. So here are some disadvantages of dome-shaped LED. As it is very expensive and not a very practical method to make the shape of the PN junction like a dome, so the semiconductor is made into the semiconductor is encapsulated into a dome shaped transparent medium which has higher refractive index than that of air. Next we have SLED or Birus LED. In SLED, the radiation is emitted through the back of the diodes, that is through the substrate. The metal layer for the positive contact is used as a heat sink. Silicon dioxide acts as an insulating layer which minimizes the contact area of the anode to the LED for increasing the current density and decreasing the active area of the LED. So here are some disadvantages of SLED. Due to the high current density, the active region of the SLED generates excessive heat, which raises the temperature of the device. And due to this rise of temperature, some problems might occur. Some of the problems are the wavelength distribution of the emitted light changes with the temperature. The rate of non-radiative recombination increases, which in turn decreases the output radiation. And the lifetime of the LED decreases due to high output power.
Hello everyone, myself Misbahur Rahman, and I'm going to discuss the rest of the presentation. Now let us see edge emitting LED or ELED. The LED which emits from the semiconductor is called edge LED. The active region of the edge LED is a narrow strip. ELEDs are capable of coupling enough power into single mode fiber. Now let us see comparison between edge LED and SLED. ELEDs typically are more sensitive to temperature fluctuations than SLEDs. ELEDs couple more power into small numerical aperture fibers than SLEDs. ELEDs emit power over a narrower spectral range than SLEDs. Superluminescent LED. A superluminescent diode SLED or SLD is an edge-emitting semiconductor light source based on superluminescence. It combines the higher power and brightness of laser diodes with the low coherence of conventional light-emitting diodes. Its emission band is 5 to 100 nanometer wide. A superluminescent light-emitting diode is similar to a laser diode based on an electrically driven PN junction that, when biased in forward direction, becomes optically active and generates amplified spontaneous emission over a wide range of wavelengths. Like most semiconductor devices, a SLED consists of a positive section and a negative section. Electrical current will flow from the P section to the N section and across the active region that is sandwiched in between the P and N section. During this process, light is generated through spontaneous and random recombination of positive and negative electrical carriers and then amplified when traveling along the waveguide of a SLED. The PN junction of the semiconductor material of a SLED is designed in such a way that electrons and holes features a multitude of possible states with different energies. Therefore, the recombination of electron and holes generates light with a broad range of optical frequencies, that is broadband light. Now let us see disadvantages of superluminescent LED. SLEDs lack optical feedback so that no laser action can occur. Even small amounts of back reflections are amplified inside the SLED chip, producing optical power levels of several tens of milliwatts of the back facet, which may destroy the SLED device. SLEDs should be carefully protected against external optical feedback. Superluminescent light emitting diodes are sensitive to electrostatic discharges and current spikes. Based on semiconductors used, there are two structures of LED: homostructure LED and heterostructure LED. In homostructure LED, the N-type and P-type semiconductor are made from the same semiconductor material. There are two main drawbacks of homostructure LED. The electoral hole recombination takes place in the various directions over a large area, so it requires a high current density. This type of LED radiates broad light beam. This makes the coupling of light into an optical fiber inefficient. This is the structure of a heterostructure LED. Heterostructure LEDs are made from two or more different types of semiconductor materials, each having different bandgap energy. Two basic principles are involved: carrier confinement and optical confinement. In carrier confinement principle, this is achieved by placing a semiconductor having a lower bandgap energy in between two layers of another semiconductor material having higher bandgap energy. Electrons injected from an N-type aluminum gallium arsenide confront an energy barrier at the junction where gallium arsenide and P-type aluminum gallium arsenide meet and are reflected back into the active region. The same mechanism works for holes also. The conduction of light in one direction, which is optical confinement, is achieved because gallium arsenide has a refractive index which is higher than the surrounding layer. Such a structure is called a double heterostructure LED. Now let us see some applications of LED: indicators and signs, lighting, data communication and other signaling, sustainable lighting, laser energy consumption. Thank you.